Steinhauer here. Welcome back. Thought I'd begin today's class with some review questions about rotation curves because they are a little confusing and more practice always helps. So I've got 4 different examples of rotation curves. And to remind you, rotation curves are a plot of orbital velocity, how fast something is moving around in a circular motion, as a function of distance from the center of that thing. And here we've got an unusual carousel where different tracks of horses are moving at different speeds as we move out from the center of this carousel. So the question first is, which of these rotation curves corresponds to the actual motion seen here? Again, take a look, make a guess, write down your answers, justify your answers, and we'll come back and talk about what the right answers are. Okay, we want a diagram that plots how fast these horses are moving as a function of distance from the center. And so you can see the first inner loop is moving pretty fast, the second one's moving slower, the third one's moving faster, and the fourth one's moving slower. So we need one that starts high, low, in that order. This one clearly does not do that. This one does, high, low, high, low, high, low, high, low, high, low, high. So we've narrowed it down to B or C that follows the general pattern of high at the middle, and then lower, and then higher, and then lower again. So which of these 2 is the best guess? Well, now we just have to figure out, are track 1 and 3 moving the same speed? Is track 4 moving a lot slower than track 3? And the answer to that question is certainly no. Certainly, track 4, even though it has a longer distance to travel, these horses are actually passing the horses in track 2. And so the horses in track 4 must be moving quite a bit faster than the horses in track 2, and that's certainly not the case for B. So we're left with C, where track 3 is the fastest, and that certainly seems to be the case. It looks like track 3 and track 1 are almost moving around at the same period, but obviously track 3 has a lot further to go, so that tracks well. And then track 4 is moving a little bit faster than track 2, and that also tracks as well. So it looks like C is the answer. High, then low, and then even higher, and then not quite as low. If we show the answer, C is in fact the right answer. Okay, let's go to the next one, a spinning pizza. Here we have pepperoni on a spinning wheel. A pizza wheel. What is the rotation curve? What does the rotation curve of this thing look like? Just follow one of these pepperonis and think about how fast they're moving around as a function of how far they are away from the center of this pizza. Go ahead and make your guess. Okay, well, I'm going to show the hint, and let's see if that makes any difference. I guess it doesn't. There's some crazy equations on here. The point, though, is that the velocity is the circumference, which is how far you are away from, how far it is around in your orbit, divided by the period. And the circumference of a circle is 2 pi times the radius. The period is, important point thing is the period is the same for all of these points. Let me hide this again. This is rotating as a solid pizza object, right? So all of these pepperonis are taking exactly the same amount of time to rotate around once. And that's really what solid body rotation is. So this period is constant in this case. 2 pi is constant. And so these constants, V is just proportional to R. V, since these pepperonis on the outside are moving further in their orbit in the same amount of time, they must be moving faster. And they're moving faster in a linear fashion. This is a linear relationship. V equals some constant times R. And which one of these is a linear increasing relationship? That has to be B. This is the only thing it can be for a spinning solid body object like this. Okay, the other 2, the next 2, this one's a planets. We have the planets in their orbit, although not quite to scale, but they are to scale in terms of how fast they're moving, right? Mercury, Venus, Earth, Mars, and Jupiter, the first 5. And again, this is a situation, this is a Keplerian orbit. This is gravitational orbits where all of the mass of the system is located at the center, in this case in the sun. And in this case, Mercury is moving faster than Venus, moving faster than Earth, Mars, and Jupiter. And that is not a linear downward trend, but it is a curving downward trend like this. So this is a Keplerian curve, looks like this. That's something you should just know. The answer is A. What does it look like for the Milky Way? We talked about this in the last class also. Again, this is also due to gravity, but it's not Keplerian because as you move outward in the galaxy, you encounter more and more mass. There's more and more mass interior to your orbit. And that's what affects how fast you orbit the galaxy. And so again, this is one you just need to know. The rotation curve is fairly flat after you get outside of the initial weirdness of the center of the galaxy, and that looks a lot like this. Fairly flat, not changing much as you go even from the very center outward to the very edge of the Milky Way galaxy. So there you have it. Hopefully rotation curves make a little more sense now.